Alright, hey everyone. This is my video on Minkowski's inequality for sums. Okay, so the statement of Minkowski's inequality is as follows. So we let x and y be in the LP spaces, where p is greater than or equal to 1. Then the following statement holds. Okay, so just a reminder, the LP spaces are basically the set of sequences such that the p norm here is finite. If we only consider real sequences, then we get the real space LP, and similarly for the complex sequences. Okay, so on to the proof of Minkowski's inequalities. So without loss of generality, we can consider the real space LP for p greater than or equal to 1 in two separate cases. Our first case is when p is equal to 1. So for p equals to 1, we have that the sum from I equals 1 to infinity of the absolute value of xi plus yi is less than or equal to the sum from I equals 1 up to infinity of absolute value of xi plus the absolute value of yi by the triangle equality for real numbers. This is then, you can then separate out the sum, and so you get the following expression. Alright, so now since x and y are both in the L1 space, both terms on the right hand side above are bounded, and so the left hand side is also bounded. As the left hand side above is also a series of non-negative real numbers, as we are taking the sum over absolute values, it follows that the series on the left hand side converges in the real numbers, hence the case p equals 1 is proved. We now consider the second case where p is greater than 1. So firstly, we note that the absolute value of xi plus yi to the power of p can be decomposed as the absolute value of xi plus yi times the absolute value of xi plus yi to the power of p minus 1. And then by using the triangle inequality, we have this equation here. If we sum over from I from 1 to a fixed n in the natural numbers, we have that the sum from I equals 1 to n of the absolute value of xi plus yi to the power of p must be less than or equal to the sum from I equals 1 to n of the absolute value of xi plus the absolute value of yi, all multiplied by the absolute value of xi plus yi to the power of p minus 1. And then again, we can separate out the terms in the sum as follows. Now, at this point, we will invoke Holder's inequality, where p is greater than 1, and p and q are conjugates, i.e. 1 over p plus 1 over q is equal to 1. Okay, so now, using the properties of the absolute value for real numbers, we have that we can take the power of p minus 1 inside the sum, inside the absolute value here, and then we can pull the other term inside the same absolute values. Then, by invoking Holder's inequality, we have the following inequality. And now we use the fact that 1 over p plus 1 over q is equal to 1, so that pq is equal to p plus q, and so p minus 1 all multiplied by q turns out to just be p. So hence, the sum from I equals 1 to n of the absolute value of xi times the absolute value of xi plus y to the power of p minus 1 is less than or equal to the sum from I equals 1 to up to n of the absolute value of xi p all to the power of 1 over p, and similarly the second term is the sum from I equals 1 up to n of the absolute value of xi plus y to the power of p, and then that all to the power of 1 over q. We can use Holder's inequality again on the second term in star, and we end up with our expression 2 by similar logic. So now if we substitute our equations 1 and 2 back into star, we end up with the following inequality. Yep, here. So if we then divide both sides by the common factor, well, not the common factor, but by the factor of the sum from I equals 1 to n of the absolute value of xi plus yi to the power of p all to the power of 1 over q, we have the following inequality here. Again, we use the fact that 1 over p plus 1 over q equals 1, so that 1 minus 1 over q is equal to 1 over p. Hence, we arrive at this result, which looks like Minkowski's inequality, but instead of for a finite sum to a fixed n. If we now let n approach infinity, and note that x and y are both sequences in LP space, on the real LP space in this case, so that both their p-norms are finite, we see that the p-norm of x and the p-norm of y are both series of non-negative real numbers which are bounded. So hence both these series converge, and the sum of these series also converges. So then, thus, we have that the sum from I equals 1 to infinity of the absolute value of xi plus yi to the power of p, all to the power of 1 over p, is less than or equal to the sum from I equals 1 to infinity of the absolute value of xi to the power of p, all to the power of 1 over p, plus the sum from I equals 1 up to infinity of the absolute value of yi to the power of p, all to the power of 1 over p. Hence, this shows that the left-hand side converges, and so we have proved Minkowski's inequality. How long was that?